All right, here we'll begin with approximating definite integral using left Riemann sum. So now we started working on the definite integral, but we'll not be able to find the exact value. We'll be approximating the value of the definite integral. So whenever we talk about the Riemann sum, it is used in approximating the area under the curve. So whenever we need to find the approximate value of the area under the curve, we use the Riemann sum. And that area under the curve will also be equal to the value of the definite integral. So it is used in approximating the area under the curve or the value of definite integral. So that is the definition of Riemann sum. So whenever you are asked to calculate the Riemann sum or find the Riemann sum, you are approximating the area under the curve, or you are finding the value, or you are approximating the value of the definite integral. The first type of Riemann sum that we are exploring today is the left Riemann sum. So here is the definition for that. Suppose a function y equal to f of x on the closed interval AB, which is divided into n subintervals of equal length delta x. If delta xk is the point in the kth subinterval for k equal to 0, 1, 2, 3, 4 up to n, then the area between the curve y equal to f of x and the x-axis bounded by x equal to a and x equal to b is given by this formula here. Okay, if I just read that definition, it doesn't make a lot of sense. So I'm going to explain this using a diagram here. So for that, I'm going to draw a function. So let me create the vertical axis, that is y-axis, horizontal axis, that is our x-axis. And then let's draw a function. Say, for example, there is a function, and this function is y equal to f of x. So suppose a function y equal to f of x on the closed interval AB. Now we are looking at this function from x equal to a here. This is at x equal to a up to x equal to b. From x equal to a to x equal to b on the closed interval. The function is well defined in this interval. And then this is divided into n subintervals of equal length delta x. So what we are doing is this interval from a through b is divided into little subintervals, and there are n subintervals. So that is the first one, second, third, fourth, fifth, sixth, and so on. So you can see from the first point a, from here, from A up to here, that is the first interval. And then that is the second interval. That is the third interval, fourth interval. We continue like this, and we are creating n subintervals. N can be any finite number. So we are creating n subintervals of equal length delta x. Suppose the length of any interval is delta x. That is the length of any subinterval. If xk is the point on the kth subinterval, for example, this is the first subinterval, second, third, and so on. If this is the kth subinterval, okay, if we consider this one in the middle as the kth interval, let me write that. If I consider that as the kth subinterval, where k is a counting number, we go up to n, then the area between the curve y equal to f of x, here is the curve y equal to f of x, and the x-axis, here is the x-axis, bounded by x equal to a and x equal to b. So if I'm talking about that area, that is the total area under the curve over here. So if I want to estimate that area, we use the Riemann sum. And here what I'm going to do is I'm going to use the left Riemann sum. When we say left Riemann sum, or the idea in Riemann sum is we try to make the rectangles. For example, if I go to this kth interval, this is my kth interval. You can see, let me say it a little bit. This is my kth interval. So in that kth interval, in order to find the approximate area of this rectangle here, we create a rectangle from the left end. That's why it is called the left Riemann sum. So we go to the top of the left end, and then we try to make a rectangle like that. You can see here it is a little bit above that, and that's okay. Here in this one, if I want to make a rectangle using the left end, you can see my rectangle will be like that. So what I have to do is I have to find the area of this rectangle, area of that rectangle, and then I have to find the area of this rectangle. You can see it is a little bit above that function. Area of the next rectangle there from the left end. I'm overestimating there. Area of the left rectangle from the left end like that. This rectangle. Similarly, we have to find the area of this rectangle from the left end. So it will be just like that. I'm trying to approximate the area under the curve. Area of this rectangle will be, if I complete the rectangle using the left side, it will be just like that. That is the area I'm counting. And then for this one, in my case, this is the last one. From the left end, I have to make a rectangle, and that is the area. So you can see, in order to find the area under the curve, what I'm doing is I'm making a lot of rectangles, and I have to add the area of all these rectangles. I have to add the area of all these rectangles. So if I want to find the area of this rectangle, it's in the kth position. If it is the x of k is the point here, the height of the rectangle is the value of the function. So area of this kth rectangle in the middle, this one, let me do it like this so that it will be a little more clear. If I want to find the area of that rectangle, which I make it a little more dark there, area of that rectangle will be, the width of this rectangle is delta x, and height of the rectangle, because it is in kth position, you can say that is xk, and the height is the value of the function, which will be f of xk. F of xk times delta x, because width times height will give you the area of that rectangle. And then here we have n rectangles. So what I have to do is I have to add areas like this. Adding means sum, you can see here, sum of this one from k equal to 1 through n. How many rectangles are there? 1, 2, 3, 4, 5, 6, 7, 8, so on up to n. So if you add that, that is the approximate area under this curve. Since I make the rectangle from the left, that's called the left Riemann sum. And you can see over here, I'm overestimating the area. I'm calculating a little more than the area under the curve. And over here, I'm underestimating. I'm leaving these little areas over there. That means this side, I'm calculating a little more area. On this side, I'm calculating a little less area. On the whole, it will be approximately equal to the exact area under the curve. So area under the curve is the value of the definite integral. So if I want to integrate this function from a through b, this is how I write the definite integral. Integration from a through b f of x dx is equal to this sum. This sum here is called the Riemann sum. K equal to 1 through n f of xk delta x. That is the Riemann sum. And the way we find xk differs from a Riemann sum to the other. In case of left Riemann sum, xk, that is the kth particle or kth position, is equal to a plus, a is the lower limit of the integration or the lower boundary for the area, plus k minus 1 times delta x. Once we have everything set up in this format, we can use our calculator and evaluate the Riemann sum. For example, in this figure here, I have a quick illustration for the function y equal to x squared. This graph here is the graph of the function y equal to x squared, and it is defined on the interval 0 through 3. It is defined on the interval 0 through 3. You can see it is from here, it's 0 up to 3. So a equal to 0, b equal to 3, from 0 up to 3. Then if I want to find or estimate the area under the curve, I have to divide this region from 0 through 3 up to a finite number. And in this case, what I have done is I have taken n equal to 10. So 10 subintervals are there, you can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, and here is the other one, very small, 10. So n equal to 10. So this is the quick example of the illustration or the graph for y equal to x squared on the interval 0 to 3 with n equal to 10. I have constructed the rectangles for left Riemann sum. But in order to perform the actual calculation, we have to set up the Riemann sum in this format here. You may want to highlight that in your note catcher. So this is the proper format that we'll be using. So by using this one, once we set up the integral or set up the area in this format, we can use our TI-84 calculator to get the proper result. So that is the introduction to the left Riemann sum, or approximation of definite integral using left Riemann sum. Example, evaluate the left Riemann sum of f of x equal to x squared plus 1 between x equal to 0 and x equal to 30 using n equal to 30 subintervals. So in order to find the Riemann sum, we have the formula sum is equal to summation k equal to 1 through n f of xk times delta x. That's our formula. So what we need to do first is we need to find everything required in this formula. So we are going to begin with delta x. So here, delta x is the size of each interval. So interval is from 0 up to 3, and that is divided into 30 subintervals. So whenever you want to find delta x, it will be b minus a divided by n. So in this case, it is 3 minus 0 divided by 30. Because we want to divide this interval from 0 through 3, so the total distance from 0 to 3 will be 3 minus 0, and that is divided into 30 equal parts, so we divide by 30. So that is equal to 1 over 10. That is delta x. So we got delta x. After we have delta x, next I need is xk. Xk for the left Riemann sum, because we are asked to evaluate using the left Riemann sum. And xk for left Riemann sum is a plus k minus 1 times delta x. So if I simplify this, a is 0, 0 plus k minus 1 times delta x. Delta x is 1 over 10. 1 over 10. So I get k minus 1 divided by 10, because k minus 1 times 1 over 10 is k minus 1 over 10. That is xk. So we have we have delta x, we got xk. Now I need f of xk. F of xk is equal to, our function is x squared plus 1. So it will be xk squared plus 1, which is equal to xk, we got it here, it's k minus 1 over 10. So it will be k minus 1 over 10 squared plus 1. So we have all the requirements. We have xk, delta x is here, we have xk here, and then f of xk is here. So once we have everything ready, we can use this formula and find the value of Riemann sum. Now, the Riemann sum using the left Riemann sum, in this case we are using the left Riemann sum because xk is a plus k minus 1 delta x. That is equal to summation k equal to 1 through n. So in this case, k equal to 1 through n is 30. K equal to 1 through 30. And then what I need is f of xk multiplied to delta x. F of xk is this one. F of xk is here. K minus 1 over 10 squared plus 1. That is f of xk. And we have to multiply this by delta x. F of xk multiplied to delta x. Delta x is 1 over 10. 1 over 10. Now we can type this in our calculator and approximate the value. So if I type this in my calculator, the result will be approximately 11.555. So this is how we can approximate the area under the curve using the left Riemann sum. In this case, as our function is x squared plus 1, if you want to illustrate that, let me quickly draw the graph here. That is my vertical axis. Here is my horizontal axis. We are talking about the function x squared plus 1. So x squared function shifted 1 unit up, and it is from 0 up to 3. So I can draw like this. This is y equal to x squared plus 1. That is my x-axis. That is y-axis. This is origin. And I want to estimate the area from x equal to 0 to x equal to 3. X equal to 0 is here up to x equal to 3. X equal to 3. And then I want to find this area. How much is this area? In order to find this area, what we are doing is we are constructing 30 small rectangles. We are finding the area of each rectangles and adding them. And the quick process is this one. So that is the approximate area. Remember that this area which is here is the approximate area, because Riemann sum will give you the approximate value of the area. The approximate area is 11.555. If you want to know the exact area is 12. We are going to learn how to evaluate the definite integral later on. And when we know how to evaluate the definite integral, we'll be able to find that exact area. Here, we are just approximating the area under the curve using the left Riemann sum. Example, approximate the definite integral 0 through 2 of x cubed plus 1 dx using the left Riemann sum with n equal to 50. So here we want to approximate the definite integral. And you know that when you're approximating the definite integral with the Riemann sum, your formula is always summation k goes from 1 through n f of x k delta x. Whether you find the Riemann sum or you approximate the definite integral, the formula is the same. So that is my formula. So what I need to do is I need to find delta xk and then xk, first delta x, then xk, and use that xk to find f of xk. Then we can set up the formula to evaluate the integral. So let's begin with delta x here. Here delta x is b minus a divided by n. We are integrating from 0 up to 2. So a is 0, b is 2. So it will be 2 minus 0. And we are dividing it into 50 subparts divided by 50, which is equal to 2 over 50 or 1 over 25. That is your delta x. Once you have delta x, next thing we need to find is xk. xk. Remember, for the left Riemann sum, your xk is given by this formula, a plus k minus 1 times delta x. Now you can plug in the values. Your a is 0 plus k minus 1 times delta x. We calculated here. It's 1 over 25, which is equal to k minus 1 over 25. So once we have the value of xk, we can find f of xk. Now f of xk is, f of x is x cubed plus 1. So f of xk will be xk cubed plus 1, which is equal to xk, we got that as k minus 1 over 25, cube of that plus 1. Because xk is k minus 1 over 25. You plug in and cube it plus 1. So that is the value of the function. So once we have everything ready, now we can approximate this definite integral. Now, let me write that down. Now, the definite integral from 0 through 2 of x cubed plus 1 dx will be approximately equal to, because we are approximately equal to the sum from k equal to 1 through n. In this case, n is 50. And then we need f of xk. F of xk is this one, which is k minus 1 over 25. cubed plus 1. And then we have to multiply by delta x. Delta x is 1 over 25. So this will be equal to, if I simplify this using calculator, it will be 5.8416. You can try that later on. 5.8416. So that is the approximate value of the definite integral 0 through 2 x cubed plus 1 dx. The exact value of this definite integral will be 6, and you'll learn how to evaluate that later on. But for now, using the left Riemann sum, the approximate value of this definite integral is 5.8416. All right, approximating definite integral using right Riemann sum. We already know the definition of Riemann sum. If you want to recall it again, Riemann sum is used in approximating the area under the curve or the value of definite integral. Okay, it is used to approximate the area under the curve or to estimate the value of definite integral. And here I'm going to talk about the right Riemann sum. So I'm going to illustrate with an example or with a graph first. So if you also want to add the graph to your note catcher, you can do that. So that's my graphing grid. Horizontal axis or x-axis is there. The vertical axis or y-axis is here. I'm going to take a function. Say, for example, here is a function, and this function is y equal to f of x. So suppose a function y equal to f of x, which I have shown here, on the closed interval from x equal to a to x equal to b. Suppose the lower end that I'm interested in is at x equal to a. So this point on the x-axis is x equal to a. And I'm going up to this point on the y-x-axis, which is x equal to b. On that closed interval is divided into n sub-intervals of equal length delta x. So again, the interval a through b is divided into n sub-intervals. So let me divide that. That's suppose 1, second interval, third interval, fourth interval, fifth interval, and so on, all the way up to nth interval. So we have these intervals, and remember that the width of the interval must be equal. And we see that if we are taking a kth interval, for example, if this is my kth interval, for the kth interval, this one, the width of the interval is delta x, and it will be same for all of them. And the height of this interval in the kth position, the height will be f of xk, because our function is f of x. So area of this kth interval will be delta xk multiplied to f of xk. If we find the area of all of them and add together, that will be the Riemann sum, or that will be the approximate area. But here, while constructing the rectangle, there is a little bit of a different trick compared to the first one. What you do here is, in order to construct the rectangle, since it is the right Riemann sum, for example, for the first interval, we start from the right and we make a rectangle like this. From the right point, we make a rectangle like that. So that is the first rectangle. We find that area. Then we go to the second. We construct the rectangle from the right top. We complete the rectangle from the right top like that. And then we find that area. And then we add it. We do the same with the third one. We do the same with the fourth one. So you can clearly see over here, I was underestimating the value of the area under the curve. Now I started overestimating, so it will be approximately the same. So for this one, if I use the right top and complete the rectangle, it will be a little bit more than the required area. So overestimating there. Here also, if I do it from the right, that will be overestimating. This will also be overestimating when I do it from the right, just like that. So you can see the concept is exactly the same, but here when we are completing the rectangle, we do it from the right. And also everything is same here except xk, because we are doing to the right. Your xk is a plus k delta x. In left Riemann sum, it was a plus k minus 1 delta x. But for the right Riemann sum, it is a plus k delta x. For this function, which I have illustrated here, our function is y equal to x squared. Okay, y equal to x squared on the interval from 0 through 3, 0 through 3, with n equal to 10. With n equal to 10, you can see if you want to count, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and here is a very short rectangle, 10. And you can see in each rectangle, for example, if you consider this rectangle here, I constructed the rectangle, or I completed the rectangle from the right top. You can see like that. So all these rectangles are constructed based on or to fit the property of the right Riemann sum. So that is the fundamental idea about approximating the definite integral using right Riemann sum. Example, approximate the definite integral 0 through 3 of x cubed minus 1 dx using the right Riemann sum with n equal to 20. So first, let me write the formula. Whenever we want to approximate the value of definite integral from a through b of a function while integrating with respect to x, this will be approximately equal to the summation k equal to 1 through n f of x k delta x. That's the formula. Since we are using the right Riemann sum, your xk will be a plus k times delta x. So we are going to find all these values, delta x, xk, then f of xk. Then we'll be ready to use this formula to approximate the value of that definite integral. So let's begin with delta x. Here, delta x is b minus a divided by n, which is equal to, in this case, as we are integrating from 0 to 3, a is 0, b is 3. So it will be 3 minus 0. And then we are dividing that into 20 equal intervals. So we divide that by 20. 3 minus 0 is 3 divided by 20. That is the value of delta x. Once we have delta x, we need to find xk, which is given by this formula. Xk is a plus k times delta x, which is equal to a is 0 plus k times delta x is 3 over 20, and that is equal to 3k over 20. That is the value of xk. Once we have xk, we can now find f of xk. That is, we have to plug in xk onto that function. So f of xk is equal to, f of x is x cubed minus 1. So f of xk will be xk cubed minus 1, which is equal to, xk is 3k over 20. We have to cube that and then minus 1. Now we have everything ready. All we have to do is we have to plug into the formula to approximate this definite integral. Let's do that. Now the value of the definite integral from 0 through 3 of x cubed minus 1 with respect to x will be approximately equal to the sum where k goes from 1 up to n is 20. F of xk is 3k over 20 cubed minus 1 times delta x. Delta x is 3 over 20. Now we can type this in our calculator to get the value. So if we type this in our calculator, it will be approximately 19.3256. 3256. And this estimation will be a little bit of higher estimation or overestimation, because the exact value of this definite integral will be 17.25. It is a little bit high. So if we want to make the value closer to the correct value, what we have to do is we have to increase the number of subintervals. Here, the number of subintervals is only 20. If you go to 30, 40, 50, 60, or so on, then it will start becoming more and more accurate. In general, when n is infinitely large, if you make infinitely many subintervals, in that case, the approximate value will be equal to the exact value. Or we can say when n is infinity, you'll be able to find the exact value of the definite integral using the Riemann sum. Example, evaluate the right Riemann sum of f of x equal to x cubed minus 6x on the interval from 0 through 3 using n equal to 25 subintervals. We are using 25 subintervals and we are approximating the area under the curve using right Riemann sum. So formula to find the Riemann sum is as equal to summation k equal to 1 through n f of xk times delta x, where xk is a plus k delta x. So we are going to find all the requirement first, and then we'll fit into this formula. So first I need delta x. That's where we are going to begin. Here delta x is b minus a over n. We are calculating the sum or area from 0 through 3. So a is 0, b is 3. So b minus a will be 3 minus 0 divided by n is 25, which is equal to 3 over 25. That is your delta x. Now next we are going to find xk. Xk is given by this formula, a plus k delta x. A plus k times delta x. A is 0 plus k times delta x is 3 over 25. So that is equal to 3k over 25. That's the value of xk. Now we need f of xk. So f of xk is equal to f of x is x cubed minus 6x. So f of xk will be xk cubed minus 6 times xk. Now let's plug in the value. This xk is 3k over 25. So 3k over 25 cubed minus 6 times xk is 3k over 25. So that is the value of f of xk. Once we have all of these ready, then we can plug into this formula. If you want to simplify this further, you can definitely do that. But if you want to leave it like this, that's totally fine. I'm just going to leave it here and plug into the formula. So now let's plug into the formula. Now the Riemann sum or the area under the curve will be approximately equal to summation k equal to 1 through n is 25 in this case. F of xk is this one. So let me write that, 3k over 25 cubed minus 6 times 3k over 25. That is f of xk multiplied to delta x. Delta x is 3 over 25. 3 over 25. So this will be equal to, if I use my calculator and simplify this one using calculator, the result will be negative 6.1776. So that is the approximate value of the area. And since we are talking about the area, the negative sign indicates that the area, the region is below the x-axis. That is the meaning of that. All right, approximating definite integral using midpoint Riemann sum. You already know the definition of Riemann sum. If you want to look at it one more time, Riemann sum is used in approximating the area under the curve or the value of definite integral. That's why I define it like this. Riemann sum is used in approximating the area under the curve or the definite integral. So that's where you'll use the Riemann sum. I'm going to illustrate the midpoint Riemann sum here by drawing a function. So you may also consider adding this in your note catcher if you want. That's my vertical axis. This is my horizontal axis. Suppose there is a function y equal to f of x. And what I am going to do is I'm going to study this function from x equal to a on the x-axis, x equal to a to x equal to b, x equal to a to x equal to b on the closed interval from x equal to a to x equal to b. You'll see that the definition is very similar to left and right Riemann sum. Suppose a function y equal to f of x on the closed interval ab, which is divided into n subintervals of equal length delta x. Xk is the point on the kth subinterval, where k is from 1 through n actually. That's not from 0 through n. It is from 1 through n, because we started counting the interval from 1, k equal to 1, k equal to 2, and so on. So that's from 1 through n. And if you want to approximate the area, over here, this area, the way we do that using the midpoint Riemann sum is like this. First, we divide this into n subintervals. That's the first one. Second interval. Third interval. We go up to nth interval. Then the way we find we complete the rectangle is a little different here. What we do is, we'll not, for example, if we're looking at this one, we'll not use the left end or the right end. Instead, we use the point in the middle. We use the point in the middle. We go up like this. And then from here, we go towards both sides and complete the rectangle. See, we are using the middle point and we are completing the rectangle. That is the first rectangle. We do the same thing on the second. We go from the midpoint. We go here on the top. Then we go left and right. We complete the rectangle. Like that. Same thing. From the midpoint, we go towards the both end. Complete the rectangle. We find the area of that rectangle and add it. Here also, we go to the midpoint towards the left and right. Complete the rectangle. Find the area of that. And the same thing with the last one. And we add all the areas. When we say add, we use the summation like this. Okay. Summation k equal to 1 through n f of x k delta x. And since this is the midpoint, in order to find the point in the middle, which is halfway through, xk is calculated using this one. Xk equal to a plus k minus half delta x. Okay, that is the formula that we'll be using. And here is the quick illustration using a formula. Using a function y equal to x squared on the interval from 0 through 3 with n equal to 10. With n equal to 10. 10 rectangles or 10 subintervals are made here. You can count 1, 2, 3, 4, 5, 6, 7, 8, 9, and the shortest one, 10. But the way we complete the rectangle, if you look at this one, we take the middle point here, we go towards the right, we go towards the left, and we complete the rectangle. So all the rectangles are completed here using the midpoint. So this is the fundamental idea of the midpoint Riemann sum. Example, evaluate the midpoint Riemann sum of f of x equal to 8x plus 30 from x equal to 0 through 3 using n equal to 10 subintervals. So you know that the approximate value of the Riemann sum, S is equal to summation k equal to 1 through n, f of xk delta x, where xk, not delta x, where xk, because this is the midpoint Riemann sum, is a plus k minus half delta x. That's the formula to find xk. So first we are going to make everything ready, and then we are going to plug into the formula. First, let's find delta x. Here delta x is b minus a divided by n. B minus a, it is from x equal to 0 through a, 0 through 3. So a is 0, b is 3. So b minus a will be 3 minus 0. Divided by number of intervals is 10. So that is equal to 3 over 10. So that means your xk is a plus k minus half delta x, which is equal to a0 plus k minus half delta x is 3 over 10. So if you try to simplify that, you don't have to worry about the 0. 3 over 10 times k, that is 3k over 10, minus half of 3 over 10 is 3 over 20. So that is your xk. Once you have xk, you can find f of xk. So f of xk will be, f of x is 8x plus 3. So f of xk will be 8xk plus 3. So let's plug in 8. Xk is this one here, which is 3k over 10 minus 3 over 20 plus 3. Now we can simplify that. If you try to simplify this one, it will be 8 times 3, 24, k divided by 10. 24k divided by 10 is same as 12k over 5. 12k over 5, then minus, if I multiply with 8, 8 times 3, 24 over 20. 24 over 20. You can simplify 24 over 20 by dividing both numerator and denominator by 4. 4, 6, 24, 4, 5, 20. So that will be 6 over 5. And then at the end, you have a plus 3. Now, you can simplify this a little bit more. 12k over 5. And here, 3 minus 6 over 5. You may make a common denominator of 5. So if you divide this by 5, you also have to multiply by 5. That will be 15 over 5, because 15 over 5 is 3. And 15 minus 6 is 9. So that will be 9 over 5. And you can write that as 12k plus 9 and single denominator of 5. That is your f of xk. We got delta x, we got xk, and then we got f of xk. Once we have everything ready, we can plug in here and we get the value of the Riemann sum. So now let's do that. Now your Riemann sum is approximately equal to summation k equal to 1 through n. In this case, n is equal to 10. F of xk, we got f of xk here, which is 12k plus 9 divided by 5. And then we have to multiply this by delta x. We got delta x here, which is 3 over 10. We can easily evaluate this or simplify this using calculator. So if you evaluate or simplify this using calculator, it will be exactly equal to 45. So that is the midpoint Riemann sum. We know that Riemann sum will approximate the area under the normal area under the curve, okay, bounded by this one, f of x equal to 8x plus 3, the x-axis, and x equal to 0 and x equal to 3. Although the Riemann sum will approximate the area, in this case, since we are using the midpoint Riemann sum, the exact value of the area is also 45, and the approximated value is also 45. Meaning of that is the midpoint Riemann sum approximates better compared to the left and right Riemann sum. Example, approximate the definite integration from 2 through 5 of x squared plus 1 dx using midpoint Riemann sum with n equal to 35. So first, we need to recall the formula for this. So if you want to approximate the integral from a through b of f of x dx, then it is approximately equal to summation k equal to 1 through n f of x k delta x. And since we are using the midpoint Riemann sum, your xk in this case is a plus k minus half delta x. So we are going to find all these delta x, xk, f of xk, and plug into this formula to get the approximate value of this integral. So let's begin with delta x. Here delta x is b minus a divided by n. which is a is 2, b is 5. So it will be 5 minus 2 over n is 35. We are dividing into 35 subintervals. So 5 minus 2 is 3 divided by 35. 3 divided by 35. And then in next step, we need to find, after we have delta x, we need to find xk. Xk is equal to, this is xk, a plus k minus half delta x, a plus k minus half delta x, which is a is 2 plus k minus half delta x. Delta x is 3 over 35. 3 over 35, which is equal to 2 plus, if I distribute this, it will be 3k over 35, then minus, if I multiply here, so 3 times 1, 3, divided by 35 times 2 is 70, which is equal to, let me write this first, it is 3k over 35, 3k over 35, and then over here, we have 2 minus 3 over 7, 3 over 70. So if I want to subtract this, I need to make a common denominator. 2 is same as 140 divided by 70. So this is 140 over 70. In the numerator, you have 140. 140 minus 3 is 137. So that is 137. Let me write like this. Plus 137 over, in the denominator, you have a 70. So that is the value of xk. Xk is equal to 3k over 35 plus 137 over 70. If you want to simplify further, you can do it, or you can just leave it here. That's totally fine. Okay, now we are going to find f of xk. F of xk is, f of x is x squared plus 1. So f of xk will be xk squared plus 1. Xk is this one, so we need to square that. 3k over 35 plus 137 over 70 squared plus 1. Now we have everything ready. We have delta x. We also have f of xk. Now in order to approximate the definite integral, we are going to plug into this formula. Now, the definite integral 2 through 5 of x squared plus 1 dx will be equal to summation k equal to 1 through n is 35. F of xk, we got it here. This is f of xk, which is 3k over 35 plus 137 over 70 squared plus 1. And then we have to multiply by delta x, and delta x is 3 over 35. 3 over 35. So we use our calculator to get this result. So from calculator, we get the value of the integral here, the definite integral, as approximately 41.9982. So that is the approximate value of the definite integral using the midpoint Riemann sum. The exact value is 42. So you can see it is fairly accurate, 41.9982. So this is how you can use Riemann sum to approximate the value of definite integral.